I am Dr. Stefan Franzen, Professor of Physical and Biophysical Chemistry at North Carolina State University. In this episode of PChem Tips, I will examine how we can use thermal radiation to calculate the temperature at the surface of the Earth or any planet that rotates so that heat is distributed over the surface. We begin by considering the bare Earth, by which I mean the Earth without an atmosphere. Then we will consider the role played by an absorbing atmosphere. Water is responsible for the greatest absorbance of the Earth's radiation by the atmosphere. The partial pressure of water fluctuates, and it contributes to the surface temperature as a feedback term. We can treat the long-term average absorbance for water for simplicity. On the other hand, carbon dioxide plays a critical role in changes to the surface temperature because the partial pressure of CO2 is increasing every year. The increasing concentration of atmospheric CO2 is a forcing term, causing a proportional temperature increase. Let's see an overview of the problem by showing some of the data relevant to the decreasing transmittance of the atmosphere caused by increasing CO2 levels. Our first task will be to calculate the temperature of the Earth based only on the Stefan-Boltzmann law. In episode 1, I showed that the integrated Planck spectral irradiance results in the law W equals sigma T to the fourth. The Planck irradiance is a spectral function with an associated unit value, wavelength, wave number, or frequency. Spectroscopists most often use wave numbers, which are usually given as centimeters to the -1. Wavelength is the inverse of wave number, if both have the same units, for example, meters. Usually we express wave number in centimeter to the -1 and wavelength in nanometers. A convenient conversion relationship is given here with the conversion factor of 10 to the 7th because there are 10 to the 7th nanometers in a centimeter. Second, we establish that the radiation equilibrium between the Sun and Earth must be the same with or without an atmosphere. The atmosphere does have an important local effect, though. It heats the surface of the Earth, but the total power emitted by Earth must still be equal to the incident power from the Sun to maintain thermal equilibrium. This reasoning implies that the radiation flux at the top of the atmosphere is the same as the bare Earth without an atmosphere. Since the absorbance by the atmosphere removes some of the outward radiation flux, the surface of the Earth must radiate with greater power than the top of the atmosphere. I will differentiate between the temperature of bare Earth, which clearly lacks an atmosphere, and the temperature of the Earth's surface, which is always greater than that of the bare Earth because of the absorbing atmosphere. We'll call them T bare Earth or T Earth and T surface. Third, we need to see how the transmittance of the atmosphere interferes with thermal emission. The Earth's thermal emission is shown by the black curve. The focus of this episode is on the absorption by the CO2 bending mode peaked at 667 wave numbers. A first principles calculation of the CO2 spectrum is possible, but quite complicated. A much easier way for this stage in a physical chemistry course is to use the data listed in a public database, known as HITRAN. This figure shows the reduction in Planck emission by the Earth owing to the transmittance of CO2 bending. CO2 absorbance is saturated in a region near the peak, but not in the wings. As the CO2 partial pressure increases, the transmittance in the wings decreases. The transmittance is obtained by integrating the spectral irradiance over all wave numbers to give the integrated flux, both with and without CO2 at various levels, and then taking the ratio. In other words, we will integrate the black Planck curve to represent the reference flux without an atmosphere, and the red curve with its dips in it to represent the flux in the presence of CO2 absorption. Svante Arrhenius, the famous Swedish scientist, first hypothesized in 1900 that the increasing partial pressure of CO2, because of combustion, would lead to a reduction in transmittance and thereby forced the Earth's surface temperature to increase. Keeling began observing the increase in CO2 in the early 1950s, and the Keeling curve shown on this slide is now an established observation of the partial pressure of CO2, measured in parts per million, or ppm. It is increasing every year. It oscillates also due to the seasons. The Keeling curve shows the data since 1958. As of 2022, the partial pressure of CO2 was 420 parts per million. Thermal radiation explains how different planets, suns, and other heavenly bodies can be in radiation equilibrium and yet maintain different temperatures. The sun's radiation impinges on the Earth continuously. We can calculate the total power absorbed using the Stefan-Boltzmann law and the radius of the Earth. The flux will decrease by many orders of magnitude as the radiation travels from the sun to the Earth. To maintain equilibrium, the Earth must radiate with equal power. We must account for the fact that Earth absorbs as a disk and radiates as a sphere. Calculation of the temperature of bare Earth. The Earth rotates about the Sun in an elliptical orbit. We will approximate the orbit as a circle for the purpose of this calculation. This figure shows that the axis of the Earth's rotation is 23.5 degrees from perpendicular to the plane of the orbit. I mention this for completeness, but the calculation does not depend on this angle, as long as the Earth's axis is close enough to perpendicular to the plane of the orbit that the temperature is relatively evenly distributed. We assume that the Earth rotates rapidly enough that the energy is evenly distributed over the entire surface. Obviously, this too is a crude assumption. This slide also shows some important data that we will use shortly to apply the Stefan-Boltzmann law to calculation of the temperature of the Earth. While there are significant deviations from uniform temperature, the Earth does have a mechanism for distributing the temperature more evenly. Clearly, less radiation is absorbed initially at the poles, and they tend to be significantly colder than the equator. In an ice age, this would be a very large effect, but presently the oceans play a major role in equalizing the energy distribution over the surface of the Earth. The conveyor belt is a system of enormous undersea ocean currents that cause cold water to flow towards the equator and warm water to circulate in the northern regions of the globe. Thermal emission will clearly differ at the poles, but for most of the Earth's surface, the emission is reasonably similar. The radiation flux that reaches the Earth impinges on a disk, which is how the Earth looks when viewed from the Sun. For this reason, the total incident power received by the Earth is the flux of the Sun's radiation in watts per square meter, multiplied by the cross-sectional area of the Earth. In the field of solar energy conversion, the name for the Sun's radiant flux that reaches the Earth is the solar constant. To calculate the solar constant, we begin by using the known temperature of the Sun, 5,780 Kelvin, the radius of the Sun, which is 700,000 kilometers, and the radius of the Earth's orbit about the Sun, which is 150 million kilometers. The Sun's radius and Earth's orbital radius are 7 times 10 to the 8th and 1.5 times 10 to the 11th meters, respectively. Starting with the Stefan-Boltzmann law, and using the value of sigma 5.67 times 10 to the minus 8th in appropriate units to give watts per square meter as the final answer, we multiply by 5,780 to the fourth power. The flux at the surface of the Sun is more than 50 million watts per meter squared. It is reduced by the ratio of the radii squared. We find that the solar constant is 1,376 watts per meter squared at the top of the atmosphere. This is circa 1% larger than the experimental value of 1,362 watts per meter squared. To maintain thermal equilibrium, the radiant power of absorbed sunlight striking a disk must be equal to the radiant power emitted by the spherical surface. The identical dependence on radius for the cross-sectional area and spherical area lead to a cancellation of the Earth's radius in the final solution. It also introduces a factor of 4 into the equality of the solar constant and the Earth's radiation flux. I must introduce one extra effect because it is quite large. The albedo, which is the reflection of the incident radiation, prevents 30% of the total incoming radiation from reaching the Earth's surface. When we include albedo and the above geometric factors, we can obtain one compact equation that gives the relationship between the temperature at the surface of the Sun and the bare Earth. This is shown on the lower right-hand side. Using this method, we find that the temperature of bare Earth would be 254.5 Kelvin, which is minus 18.5 degrees centigrade. The equation derived for the temperature of the surface of a bare planet is valid for any planet as long as it rotates and does not have an absorbing atmosphere. Without an atmosphere, Earth would be too cold to support life. Mercury does not rotate. Venus has a very absorptive atmosphere, but Mars has little atmosphere and rotates. The model works quite well for the surface temperature of Mars. Next, we consider an analogous procedure in the presence of an absorbing atmosphere, with a transmittance called tau. The transmittance ranges from 0 to 1, where 1 means no absorption and 0 means total absorption. We will show that tau for the Earth is approximately 0.62 and getting smaller every year. Looking from space, the atmosphere is truly a thin layer surrounding the Earth's surface. The radiation balance that we described for the bare Earth must also hold when the atmosphere is present. To accomplish this, we will assume that the radiation flux emitted at the top of the atmosphere is equal to the solar constant divided by 4, exactly as it would be for the bare Earth. In this simple approach, we therefore assume that the average temperature at the top of the atmosphere is 255 Kelvin, just as it was for the bare Earth. Atmospheric experts would be quick to point out that there are 5 different layers of the atmosphere: the troposphere, stratosphere, mesosphere, thermosphere, and exosphere, and that temperatures change a great deal in these various layers. There is not a uniform cooling with height in the atmosphere, partly because of the absorption of atmospheric gases. For example, ozone is formed in the upper atmosphere and causes a significant warming at the stratopause. Nevertheless, the average temperature of the upper atmosphere is relatively low compared to the surface. The assumption that the radiation from bare Earth equals that from the top of the atmosphere must correspond to reality, or the Earth would not be in thermal equilibrium with the Sun. Since the flux at the top of the atmosphere must be the same as that of the bare Earth, and some of the thermal radiation from the Earth's surface is absorbed when an atmosphere is present, the radiation from Earth's surface must be greater than either of the other 2 fluxes. Moreover, the flux from the surface of the Earth will increase as transmittance of the Earth decreases, because there's more absorbance that will occur before that radiation reaches the top of the atmosphere. The role played by transmittance is to reduce the radiation flux gradually as it passes through an absorbing atmosphere. The larger radiation flux from the surface implies a higher surface temperature. This is the Stefan-Boltzmann law again. Now we solve for temperature, using the fact that the flux at the top of the atmosphere is equal to the flux of the bare Earth, and surface temperature is increased by the inverse of the 4th root of transmittance. So far, everything we have considered is a direct consequence of the Planck radiation law and a transmittance that is less than 1 in the atmosphere. To obtain an estimate for the transmittance, we need spectroscopic data of the species that absorb in the atmosphere. Climate scientists refer to carbon dioxide as a forcing term because the increasing partial pressure forces a change in the relationship between the surface temperature and the temperature at the top of the atmosphere. The presence of water in the atmosphere is called a feedback term. The partial pressure of water fluctuates with the season, geographical location, and weather. For simplicity, we will assume an average transmittance by water that does not change. Water comes and goes, but carbon dioxide is steadily increasing. We need to examine spectroscopic transitions of CO2 to understand its effect on atmospheric transmittance. We want to obtain the flux, which is the net radiation power emitted per square meter at the Earth's surface. The complication enters because each point on the surface radiates in a hemisphere, not just straight up. Using an averaging procedure, we can calculate the net upward flux on a radiation per square meter basis. This is the radiation flux that we will use in our model calculation. We can imagine radiation leaving 1 square meter of the Earth at the top of the atmosphere towards space, which has been reduced in intensity by absorbing gases in the atmosphere. The HyTran database consists of observations and complementary calculations of molecular spectra of atmospheric gases. Using the principles presented here, one could make predictions about the role of ozone and methane, for example. We will confine our interest to carbon dioxide. The Excel spreadsheet shows the output from the HyTran database when we selected natural abundance carbon dioxide in the range from 200 to 2,000 wave numbers. We then filtered the list to keep only 10,000 or so of the most intense transitions. Using those data, we could obtain a spectrum for the bending mode vibration of CO2 shown on this slide. The raw data are simply point values. I wrote a Fortran program that outputs a set of Gaussian functions with a spectral width of 0.13 wave numbers. There are many lines in this spectrum because rotational vibrational spectra of triatomic molecules have 3 branches, P, Q, and R, each with many lines in them. The most intense band of the CO2 bending mode is called the Q band, and it is peaked at 667 wave numbers. The molecular spectroscopy of gas molecules will be discussed in an episode on molecular spectroscopy. The spectrum of CO2 is converted to transmittance and plotted in red on this figure. On the left, I compare the shape of the transmittance of CO2 and the Planck radiation curve. On the right, I show the transmittance combined with the Planck law radiation of the Earth. One of the arguments used by skeptics of global climate change is that the CO2 absorption is saturated. They have noticed correctly that the absorption is saturated in the region closest to the peak. The transmission is 0 from around 610 to 730 wave numbers. And it is true that increasing the partial pressure of CO2 will not change this region. It is already maxed out. But it will change everywhere else, and most significantly in the wings flanking the saturated region. This figure compares the same calculation done above for 3 partial pressures of CO2, 410, 600, and 1000 ppm. Clearly, these are large changes in CO2, but conceivable levels if we do not find an alternative means of energy conversion. The changes from year to year are much more subtle, but still large enough to have an effect on the overall atmospheric transmittance. For the calculation of surface temperature, we need the transmittance at all emitted wave numbers, or wavelengths if you choose. We can obtain this by integrating the Planck curve. We use the Planck curve of the bare Earth, the one in black, as our normalization. Then we can integrate the combined transmittance Planck curves like those shown on the previous slide. This can be done very simply as a sum of all entries in an Excel spreadsheet using the sum function. Since the spacing is so small, that's really as accurate as an integral. It is evident that there are significant changes in transmittance over the range we considered. We will show that there are small changes even on an annual basis. That is concerning, since even small changes in the Earth's temperature can affect weather, rainfall, sea level, and so on. Here I have plotted the integrated Planck density for a series of CO2 partial pressures. We need to include water, as mentioned previously, and we do that at this stage by multiplying by an average transmittance of 0.7 for water. The equation on this slide justifies the approach of simply multiplying the two individual transmittances to obtain the overall transmittance. Using the total transmittances calculated by integration, we can plot tau, the transmittance of the atmosphere, as a function of the partial pressure of CO2 in parts per million. On the left, I show this for the future 100 years or so. Assuming there is no change in the rate of CO2 emission by human activities, the partial pressure will continue to increase by more than 2 parts per million each year and reach 600 parts per million in a century. The transmittance will drop from 0.62 to 0.61 during this time. The figure on the right shows a longer time frame. I have added a few much higher CO2 partial pressures on the right for comparison. While the decrease in transmittance is linear in the near term, I mean for the next 100 years, we can see that it does start to level off if the CO2 concentration is high enough. The skeptic's argument about saturation would come into effect by about 5,000 parts per million. Using the equation that relates the surface temperature under an atmosphere, T surface, to that of the bare Earth, divided by the fourth root of transmittance, we can convert the linear decrease in transmittance into a linear increase in temperature. Although this model is very simple, the temperature of the Earth's surface is obtained with reasonable accuracy. The model predicts that the average temperature of the Earth today is 286.7 Kelvin. This is an increase of 31.7 Kelvin, or degrees Celsius, relative to bare Earth. This is the so-called greenhouse gas effect that makes life possible on Earth. The second conclusion is that the model predicts a temperature increase of 1.2 degrees Celsius over the next 100 years, assuming that the CO2 parts per million increases approximately at a rate of 2.1 per year, which is the current rate of increase. This value, too, is in line with sophisticated climate models. Climate scientists have much more detailed and inclusive models, which are important for accurate predictions and understanding detailed changes in weather patterns, predicted rainfall, and so on. Our purpose is not to propose an alternative to the professionals, but to give students insight into the most basic physics so that they can appreciate what climate models tell us. Hopefully, students will also be able to speak with greater confidence on the subject once they understand the basic physics. Given the importance of this topic, this seems like a worthwhile extension of learning on the subject of thermal radiation.